we have one more presentation and then we'll have lunch. And I see some people standing behind. If you are tired, there are free seats in the front row. Please find your seat. I understand that for physical activity, sometimes it's better to stand, but as you wish. Make yourselves comfortable. And our next presentation is to be given by Peter Kovacs, again, a long-time colleague, friend, and collaborator. The light field imaging and holographic imaging lost an expert for automotive imaging. So now we are going to hear whether this was worth it. Yes, please.
Thank you very much. Indeed, I will jump around a little bit in my presentation, but the main theme is about how we use recent visual technologies in testing AD and autonomous autonomous driving and driver assistance systems at the aiMotive. So a little bit about myself and why I'm planning to jump around topics a little bit today. So I have a master's in computer science from the Technical University of Budapest, after which I was working with real-time rendering on GPUs at a CAD company, which then led me into the 3D display world at Holographica, again a Budapest-based company, where I spent almost 10 years, and that was where we have been building light field displays, one of which you can see here also at CIVIT. So this is one of the biggest displays that we have built. But during that all the development that we have done, we have been working with synthetic images for many years, only synthetic images. And then we wanted to have also live imagery, which seemed impossible for some time. But afterwards, we started building multi-camera rigs, and then we started doing real-time light field transmission from the multi-camera systems to the light field display, which eventually led to the question of light field compression and efficient distributed decompression and rendering of these light fields, which eventually led me to my PhD topic, which was around light field compression, and I actually finished my PhD here at Tampere University of Technology, my advisor being Atanas, so thank you very much for that. It was a big experience and very good to be here. And yeah, with a seemingly big shift, I then changed to a different company. At that time, it was called AidasWorks. Now it is called aiMotive, which is basically a company which was focusing on, and still does, on automated driving. And I'm also involved in the data processing part for like almost 4 years now. So a little bit about aiMotive. So it started like 10 years ago, and the main objective was to create software for self-driving vehicles. So that's what is called aiDrive today. It's an end-to-end software stack, so it basically starts where we receive the data from the raw sensors, so in this case cameras and radars, and then it ends where we issue the control commands to the vehicle, steering, braking, acceleration, turn lights, and so on. So that's what aiDrive does. Then, as we have been working on the development of aiDrive, we realized that the tools which have been available or not available were not really sufficient for our purposes. So we started to do our own tools. The first one of which was a simulator, which is today called aiSim, and it will be a main topic today. So what we have been struggling with 10 years ago was that the automotive simulators available at that time well, we're not really excelling in terms of visual quality when it comes to testing camera-based perception, and that was exactly what we needed. So we started building our own simulator, which we in the beginning kept for ourselves, but then on popular demand we started to sell it to other companies, and it's currently the best performing product of the company. The other thing we did, because AI Drive is highly dependent on AI-based perception algorithms and also increasingly AI-based path planning algorithms, we needed a data processing pipeline. And that's what aiData is, and that's the department that I was working in the past 3-4 years. We define aiData as everything between the point where the data collection vehicle enters the building up to the point where we can hand over searchable, categorized, and fully annotated data to the AI researchers, to developers, and also test engineers to do their validation things. And the last spin-out activity from AI Drive development is a little bit of an exception because it's not a software product, but it's a hardware IP. So we realized 10 years ago that OEMs are not really willing to put ordinary GPUs in their vehicles because of their power consumption, and because of the power consumption comes the heat dissipation. So they didn't like any of that. And we figured that if we had a specialized neural network inference engine for processing high-resolution images with CNNs, we could be better in terms of power consumption and also efficiency of the utilization of the chip. And this is what aiWARE is today, and it is available as an accelerator block in commercially available SoCs already available today. And one more note is that the aiMotive company was acquired by Stellantis almost 3 years ago, so now we are a part of the Stellantis companies. If you don't know, Stellantis is the concern behind maybe 14 brands, Fiat, Peugeot, Citroën, Chrysler, Maserati, and so on. I'm not going to list them all. But we are still operating independently, and we are still open and then able to use all this software with other companies outside Stellantis. So jumping back a little bit in time, when I was working in the light field display field, we started building these capture rigs that I mentioned, and in this video you can see the first light field transmission that we recorded on film. This is the CEO of Holographica logged into this HoloVisio display as we captured him with the multi-camera rig. And here you can see this is a parallel arrangement. We also are dealing with arc arrangement, so we were looking at something. Now, in case of the vehicles, we have cameras also here, but we have these cameras attached to the vehicles, and these are looking from the vehicle to the outside world. But they are not so much different. I mean, the packaging is of course different, the size is different, the robustness is different, the interface is different, but from the perspective of perception and, for example, camera calibration, they are pretty much the same. So there is so much knowledge that is transferable from one domain to the other one because of the commonality of the sensors. Of course, in case of the automotive use case, we also have multimodality. So here we need to do like a cross calibration of cameras and radars, for example. But still, the story is quite similar. And the other common topic that I apparently can't get rid of are GPUs. So I started with GPUs, I continued with GPUs in the light field display field. So in this big display, we had 72 projectors. Now, if you want to generate the image for these in real time, you need a rendering cluster because you can't squeeze out that many pixels from a single computer. And that's exactly what is on the back side of the display. And here is a sample of rendering cluster which contains uniform GPU nodes. And if we look at a self-driving vehicle, somewhere you would find an embedded GPU, or better, not a GPU, but a specialized neural network inference accelerator somewhere in an SoC. But if we look a little bit aside, then we also have to consider the data center, which we use for processing the vehicle data, because that's where we do all the post-processing. And now what happens in this data center for processing the multi-sensor data, now the configuration of this one is very similar to what we have been using for the rendering clusters. So again, there is a lot of knowledge that can be transferred between the two domains. Now, today I'm going to talk about World Extractor. So what is World Extractor? As I mentioned, we have this simulator AI sim, in which you have like empty worlds, which are based on real or imaginary places. You have the road structure. You furnish it with 3D objects, and then you populate these empty worlds with simulated actors who have some intention, and your ego vehicle has some objective to reach in order to have a successful test case. Now, the thing is that there is always the question of how real it is when you put it together from synthetic objects. And the other thing is that when you want to reproduce a problem which occurred in the real world, in a real place, and you don't have that in simulation, then what you can do, your only choice so far was that you model that place, or you ask the 3D artist team to model that place, which would typically take a couple of weeks of work for them to reproduce the road structure, to create new 3D objects which are similar or identical to the real place, and then furnish the environment with these objects, which can then be populated. So this is okay if you want to simulate highway driving, like in that case you don't have so many surroundings. But in an urban situation, especially, the surrounding does matter. It might disturb perception. It might introduce unwanted effects that you want to reproduce. So we basically had two extremes when it came to testing the AD system. The obvious choice is just using the real-world recording, in which case you just feed in the recorded sensor data as is into the software, and then you let it do the processing. It will be perfect because it gets exactly the same sensor data that it got in the real world. But the bad thing about it is that it is open loop, meaning the driving software doesn't have the possibility to react and to change its trajectory if you introduce some change to the software. You can observe that maybe the perception behaves differently, or maybe the software would have made a different decision, but it has no way to control the video file that you stored. So you can't really do anything about it. There are use cases where feeding in real-world recordings has a benefit. So, for example, for robustness testing of autonomous emergency braking, if you assume that you record 40,000 hours of driving around, trying to chase situations where there is a situation where you might or you might not need to brake. There are corner cases that you can hunt for. But assuming that your data collection drivers did not crash during the data collection, then the right reaction from the vehicle when you play back all this sensor data to the software is not to emit an automatic emergency braking signal, right? So this is one use case where the readback testing actually works and it is useful. Now, the other extreme is the fully synthetic simulation, where the realism is good, but it's not real in the end. And as I said, adding new 3D scenes involves quite a bit of human labor, so that reproducing real scenes takes some effort. So then we thought, what if using the data that we collect with these vehicles, we could bring the realistic environments into the simulation, but do so in a way that we enable closed-loop testing, so we can reproduce novel viewpoints that originally we did not capture. And that's exactly what we did. So we can now reproduce environments in the simulation, and then we can populate it with dynamic agents. And we can also simulate different weather conditions to some extent. And also we can add sensors to the simulated vehicle which didn't exist at the time of the recording. So like if we have a 360-degree capturing on the vehicle, then we can add a fifth camera if we want, which would then reproduce a viewpoint which we never captured. Or another use case is like recording data with a smaller vehicle, and then simulating what an SUV with a similar but slightly elevated sensor set could have seen in these situations. Okay, so. Just a few examples of how this looks. So this was one of the first scenarios that we reproduced with neural reconstruction and Gaussian splitting from San Francisco. So you can see that the buildings, the trees, and also the parked vehicles, those are coming from the environment reconstruction. But the dynamic elements, the dynamic vehicles, are coming from the simulation. And another example in an outdoor parking scene. So here again, buildings, trees, everything else is coming from the reconstruction, and the simulated vehicles are added afterwards. Okay, let me skip through these. Okay, so I know that there are many people dealing with nerves and Gaussian splitting, and with that it is possible to reproduce these novel views or new sensor sets. But what we added on top is that we have additional layers in the reconstructed world, with which we can reproduce also LiDAR reflections, as well as radar reflections from the environment. That's very important, that it's not coming just from the objects that we introduced afterwards, but the LiDAR and radar reflections are also present from the captured static environment. So in order to demonstrate that this thing works outside of the world of recordings that were done by aiMotive, we also executed it on the Waymo dataset, and as you can see, it produces quite nice results. And on top of the LiDAR and the radar layer, we can also embed semantic segmentation information as an additional layer of information, which then can be used for different purposes in the simulation once people are using the output of the simulation for purposes like environment perception. Then often we get the question about, okay, but how realistic it is when we are reproducing a slightly different point of view. And in our opinion, using some traditional metric for this is not really feasible because we don't have ground truth information from there. I mean, we could, but this is how it is. But in case of a driving setup, so in case of an environment perception setup, you can tell how realistic it is with respect to your environment perception algorithm or any environment perception algorithm, because one algorithm might be sensitive to one kind of degradation while another one might be sensitive to something else. So what we did is that we have taken a public data set and we have taken a public master-former semantic segmentation network, and we executed it on the original recording. And then we also executed it on another viewpoint, which is shifted 3 meters away from the original one, to see how the perception still works with this synthesized viewpoint. And there is a paper referenced afterwards from my colleagues where you can find the measurement results of this experiment. So a little bit about how it works, skipping the initial parts. So we have to run the auto-annotation techniques that we normally employ for coming up with the ground truth data for AI training purposes. And we do that for 2 reasons. One is to remove the dynamic elements, because this technique works on a static environment. And the other reason why we are doing that is that if we want to re-instantiate the vehicles that we captured in a real scenario and in the simulation, then we can. Because wherever we have seen them, if we put them back in simulation or some vehicle which is similar, then we can get back the original recording with the possibility of adding or removing additional elements or changing them, or changing the vehicle type, for example. And after that, there is a 2-step process. First, we train a NERF model, and then based on the NERF model, we create a Gaussian splitting-based model. Why we do that? The reason is that we wanted to have real-time performance, even with multiple high-resolution cameras. And with the NERF model, we couldn't achieve that rendering speed. But the Gaussian splitting-based model is able to produce real-time output. And if we train the Gaussian splitting based on the NERF model, we can achieve, at least in our experience, better results than training the Gaussian splits directly on the incoming sensor data. So this is to show how AI drive is driving in this environment. So here you can see that it is driving towards a roundabout, which we found problematic because it couldn't properly handle it. And we have seen that if we reconstruct in the environment and we put AI drive into this simulated environment, it did the exact same failure that it does in reality. And so the developers could iterate on roundabout handling, and so eventually could solve it without returning to the same roundabout with the vehicle until they said that now it is working properly. And this is how it looks from the front camera perspective. What is the input of the driving software in this case? And when they return to the same roundabout with the fixed software, they could experience that indeed the behavior was now correct, and it can handle the roundabout properly. So right now we are in the process of collecting and reproducing many roundabouts for robustness testing of roundabout handling. And to make it more interesting, I will share a few technical details. I will not go into every step, but starting with the dynamic auto annotation. So we basically have 2 separate pipelines. One is based on a bigger version of the real-time perception network. And then we have a classical multi-sensor dynamic auto-annotation path, which are then fused together. And that's how we come up with the 3D bounding boxes that you can see here from the LiDAR perspective. And you can see here from the camera perspective. So this is one input that we use. And then as we go further, we also come up with masks so that we can remove the dynamic objects, but we can keep the static objects. The reason why we keep the static objects is that we can't really see behind them. So there we would need quite a lot of guessing. So it's better to keep those, but we can eliminate them if we want to. And during the auto-annotation process, we also create an aggregated point cloud, which will then be used for LiDAR intensity map generation as well as depth supervision. But there is one more thing that we are doing, removing the shadows, because removing the objects themselves is just half of the story. If you still have the shadows on the road surface, it will look interesting, so to say. So we also have to remove the shadows from the road. Then we have a mesh, which is not the nicest mesh, but it is good enough in order to introduce a depth layer and the normal map layer, as well as a LiDAR intensity layer into the model, which can then be used for different purposes afterwards. And then we have a call map-based refinement step, because even the most precise camera intrinsic and extrinsic calibration might not be as precise as we wanted. So the output benefits from this additional step. And because we can't have like infinitely big areas modeled with this technique, we separate it into blocks, and as we are driving from one to the other, we are smoothly blending from one block to another one. And how each block looks. So in the NERF model, what we basically have is a 5-dimensional input, 3-4 position, 2-4 directions, and we basically ask the NERF model what is the color and the density if we are looking into that direction from that position. So if you know volume rendering, it's very similar to that, but here it is not an explicit 3D array representation of a volume, but it's a neural network which stores this information. However, in many of the NERF papers, you can see that they are looking at some object or looking at some compact scene. We do the opposite. So we are looking from one place to the external world, and this is how we train the nerves. And also the Gaussian splatting model. So the Gaussian splatting model is really just a large set of 3-dimensional Gaussian splats with some additional properties that, if we put them all together with their meta information, can create a visually appealing representation of the environment. Then we have some depth and normal regularization, because these models tend to pick something which looks good from the viewpoint that you captured. But there can be inconsistencies in terms of size and shape, which we want to avoid when we are reproducing novel viewpoints. So that's why we have also this regularization step to come up with better depth and normal map estimations. Okay, so when it comes to view synthesis from extreme viewpoints, so here we use a diffusion model to enhance the image quality. And with this, we go as far as up to 9 meters away from the trajectory of what the actual recording vehicle took. As you can see from this video, as we approach these extremes, especially as we are going like inside vehicles, you can see some artifacts, but this is to show what is the reasonable limit that you can achieve with this technique. And I can't help to jump back a little bit in time with this video that we took again with the HoloVisio display, where we used a very wide camera array to capture this scene. Now, if we use this technique that we are using in the automotive simulation today, maybe we could use a much lesser number of cameras and interpolate and extrapolate freely. Here I'm also referencing the 4-camera rig that we worked together with Frederick in the Muscat project. Now, to be fair, in the automotive simulation part, we are reconstructing a static world, and here we would need to do that for every single frame. So we are still not there in terms of runtime, but I'm hopeful that that this is going to happen. For the sake of time, I skip this one, and while this video is running, I'm happy to accept questions.
Perfect timing. Thanks a lot. And we are going to take questions.
Thank you. A very nice presentation. Well, what are the training times and inference times you have in doing such a video?
So normally, when we train, we train the nerve and the Gaussian split in basically one chain in the data pipeline. So as it is going through, we usually spend one or 2 days on one bigger environment, which would contain multiple blocks in it. And then during the runtime in aiSim, this is already working real time. So the rendering part of the Gaussian splits.
30 frames per second.
Yes.
Okay. Yep. Martin. Yeah.
What kind of resolution can you reconstruct with that method? Is there any limitation, I guess?
Well, I mean, it depends on the resolution of the incoming cameras that we captured, and then also how many splats we allow the modeling to create. So here there is a trade-off between rendering time and visual fidelity, and we try to automate setting it to reasonable trade-off. But I can't tell you an exact resolution number to that, because in the end it's really the visual appearance of the object. So you may be able to measure it through the faithfulness of the textures, maybe.
Yeah.
Thank you for your service. I have a question. How do you detect the shadow?
How do we detect the shadow?
Yeah.
That's a very good question. That's something for my colleagues to answer, so I will have to get back to you on that.
Okay, thank you.
Hello, thank you for your presentation. In the first presentation, we heard that realistic sensor models are important, right?
Yeah.
Do you see any challenges that aiMotive is going to address related to that? For example, radar sensors, like higher resolution radars and so on?
Yeah. So, well, I didn't mention this today, but aiSim has an API for everything, including sensor models. So it has built-in sensor models for cameras and radars and lidars that can be parameterized, or you can implement your own. But we also have interfaces to accept camera sensor models from the 3 major camera sensor providers that are active in the automotive domain. So we basically cover them all. And similarly, if there is a radar simulation model from a radar manufacturer, we can plug it into the simulation. We don't have to recreate it.
Okay. maybe no more questions, but Peter is around also in the afternoon and at the demo session. And if holographic display is working, we can also
Hopefully.
discuss light field.
Yeah, I would love to see that. Yeah.
Okay, so what follows is lunch, and you are invited to lunch on the occasion of celebrating 10 years CIVIT. Now, if you go through the upstairs door, you will be already at the restaurant. You cross the restaurant, go to directly to the windows at the end, and there is a buffet arranged for our workshop. So don't take the normal lines. You can, but we hope that the buffet is a bit better food, unless you want to remember student years. So go to the buffet at the end, have your badges so that you are recognizable as workshop attendees, and see you back at 1 o'clock. You have to be a bit, 55 minutes for lunch. See you soon.